All right, good morning. It's a nice Monday today, shiny outside, and I'm quite sure you're going to be hearing this dozens of times throughout the week, but it feels great to be back at Devoxx. And we are starting, first of all, with, well, some deep dives. Thank you for being here. Just before we get started, to get a feeling of who I'm talking to, a quick show of hands. How many of you do work with Kotlin on a daily basis? All right, more than half the room. That's really good to see. And what about coroutines, concurrency, parallel tasks? Okay, nice. Another practical tip. There is plenty of room in the, in this theater. Therefore, if you brought your laptop and if you want to follow along the live coding, or at least the code demos I'm going to show, feel free. There is a Git repository. The URL is going to show up in a moment. So if you want to follow along, be my guest. If not, do as you wish. Now, on to myself. That fellow over there holding a book is myself, with a copy of some trees who gracefully gave up their lives so that my book could be printed. I've been doing this stuff for 20 years and still counting. Thanks to globalization, I was born down south in Europe. I'm Portuguese. I'm living and working currently in the Netherlands and giving a talk to you at Devoxx Belgium. Thank you. And without further ado, let's get down to business. Now, a quick refresher for those of you who didn't raise their hands when I asked about parallel programming, concurrent flows. What on earth is that? First of all, some terminology. When I talk about a flow, I mean, of course, the flow of a program. Regardless of the sort of program we are writing, its instructions are going to be executed in some sort of sequence that hopefully makes sense in the end. Generally speaking, one can have three kinds of flows. Either they can be sequential, parallel, or concurrent. Now, the sequential part is the easiest one. It's how all of us start. The first program is sequential, and honestly, it's how we write code, unless we are forced to stop being sequential. Things pretty much happen one after the other. As time passes, each task is executed in the same sequence as it was programmed. Nothing fancy. Pretty straightforward. The other kind of flow is the parallel flow. Now, in this case, we have different tasks being executed at what looks like to us, humans, the exact same moment in time. From the machine's point of view, that may not be exactly the case, but as far as we are concerned, it happens in the exact same moment in time. This is the typical mode of operation for any distributed system. If you want to go back to computer science, any distributed system is a parallel system. There is absolutely no question that a task running in one server is running in parallel with some other task that's running on another server. And nowadays, with multi-core and truly parallel processors, that is also true in our local machines. What some people may find a bit confusing is the difference between a parallel flow and a concurrent flow. Now, in this case, things may get a bit tricky because as humans, lots of things are happening that appear to us as if they are happening at the exact same moment in time. However, at the time scale of a processor, that is not necessarily true. A processor can take a few milliseconds to do something, switch to an entirely different task, and run that task as well. To us, it looks like it was at the same time, but in fact, they ran one after the other. The difference is that they were sharing the same resource. Normally, in this case, we talk about the same processor or the same processor core, if you want to go, at that level. But the basic idea that underlies the notion of a concurrent flow is that although tasks that are being executed concurrently may appear to us as being executed in parallel because they are extremely fast, in truth, they are sharing the same processor and they are being executed one after the other. Even though in today's machines they may not necessarily share the same processor, the moment the program is switching between tasks to run them one after the other, then we are in presence of a concurrent flow. Concurrency can also occur not only when a microprocessor is being shared, but also when other resources are being shared. Now, of course, it follows logically that it is, for example, not possible to write to the same location in memory by two tasks at the exact same time. Therefore, it follows that one needs to wait for the other. At that point, concurrency is in motion. The basic or fundamental principle here is that a concurrent flow does not have multiple tasks running at the exact same moment in time at the scale of a processor. That being said, what is the fundamental unit of execution on any modern operating system? Normally we say that a thread is a unit of execution. Because if you look at the operating system itself, if you look, let's go one level deeper. If you look at modern processors, if you take a look at each core inside that processor, and depending on who built that processor, depending on how the machine is organized internally, we can say that a given machine has as many hardware threads as cores. In some machines, you may have twice as much because some cores are actually capable of running two hardware threads simultaneously. I think it was Intel who coined the term hyperthreading years ago, and that was the idea. But this means that when it comes to hardware, resources are limited. If I have let's say an 8-core processor with some sort of hyperthreading support, I can have at most 16 hardware threads in the machine. So that means the processor is only capable of doing 16 things at the same time, or roughly. If we scale it up to the operating system level, then things explode. I mean, if we look at any kind of tool that gives us the statistics about the operating system, at any point in time, we are going to see that there are thousands of threads running. And those thousands of threads, they are supported by these 16 or 32 or 64 or whatever, by this small amount of hardware threads. Now, this goes to say, or to justify, the first point that you have on screen right now, is that when we work with threads in our programs, we are working with software threads, in the sense that normally, and you will hear me say normally a lot, or generally a lot, because there are always exceptions, and it always depends. But when we create a thread on a program that we are running, it is a software thread. There is something in the operating system called a scheduler that will decide when our code is going to run and on which hardware thread, on which core. In order to share the limited amount of hardware threads across the thousands of software threads that are created by the operating system and all the programs running on it, operating systems have something called a scheduler implemented. It's something that has been fine-tuned across the years. It's extremely important. It's the thing that, whenever it has problems, makes your computer stop. And that's the one that decides when does each thread get some CPU, and the other important part, for how long. That is preemptive multitasking. The scheduler decides, okay, I have 6,234 threads, and number 139, by my math, has been stopped for a very long time, so let's give it 10 milliseconds processor time. After those 10 milliseconds are exhausted, okay, stop, and let's take to the next one. And this stopping part leads us to suspension of execution. It is the scheduler's job to start, pause, or suspend, resume, and eventually stop a thread. The problem with suspending the execution of a thread is that, well, there's lots of state associated with it. And this leads us to the third bullet point. Let's think about it for a moment. Again, let's look at the hardware and walk up from there. If we only look at the processor, we see that the processor has an internal state associated with the program. There are things called registers in the processor, small memory areas, often, depending on the processor, 8, 16, 32, 64 bytes long, that store information about the program. It stores the point of execution, normally called the program counter, and others can also be used by the program to store intermediate states. Quick show of hands to know if I should go into further detail. Has anyone here worked with actual assembly on microprocessors? Nice. All right, so those of you who raised your hands, you know what I'm talking about and are probably thinking, yeah, you should have drunk another cup of coffee. But the point is, if we look at the processor, there are registers there. And those have had their contents changed by the thread that's running. So if we want to suspend this thread and then start a new one, now we are not going to leave the data there. That's going to be overwritten by some other piece of code. And of course, then if we want to resume the first one, then where's the data? All of this state needs to be saved and restored somehow. Threads are stateful instances. And of course, let's not get started in higher level stuff like call stacks or program variables, whatever. If we compare threads with coroutines, the big difference is right there on the first line. Coroutines are cooperative. What does this mean? Now, you remember that I said a few minutes ago that the operating system scheduler decides, so it's an external entity, it decides when and where and for how long each thread runs. When we are writing coroutines, it's the code itself that decides for how long it is going to run and when will other coroutines have the opportunity to do something else. In other words, our code gets CPU time, runs, does whatever it is it feels it should do, and at the point we have explicitly, or one of our dependencies has explicitly mentioned, okay, it's time to give the CPU to someone else. Giving the CPU to someone else involves the exact same concept that we have on threads. It involves suspension of execution as well. Although, now this happens at a different level. With threads, the entity responsible for suspending execution and saving state is the operating system scheduler. We don't worry about it. It just works. When writing coroutines, the entity responsible for suspending and saving the state is our program. In the case of what we're going to see next, it's the Kotlin runtime. It knows how to store and restore state, which takes us, of course, to the next point, which is that coroutines are also stateful instances. Now, if we look at some pseudocode, and we go back to that concept that threads just like to run. Let's imagine that we have, the typical example of a producer thread and a consumer thread. Simple stuff. The producer places items on a queue, the consumer removes items from that queue. Looking at pseudocode, we have a thread with a tight loop and another one with a tight loop. One adds items, the other removes items. This works. And the reason why this works is that, again, we have that entity, the operating system scheduler, deciding when does each thread run. Now, of course, in practice, we don't want to do this. This uses up too much CPU, but it's good for a simple example. If, on the other hand, we look at a pseudocode for coroutines, then we see a small difference. The producer adds items and then gives some CPU time to the consumer. So I placed some items there. Now let's allow others to take them from the queue. The consumer then gets its turn to run, removes the items from the queue, and when it is finished with them, decides, okay, Now it's time to give some CPU time to the producer. The producer gets an opportunity to run, places some items, etc., etc., etc. It's a big ping-pong game with CPU resources. Looking at this concept, this is a good example of cooperation. Every single coroutine allows others to run, which means, and we are going to actually see this in practice later on, which means that on top of the normal concerns about parallelism and concurrency, we now need to either implicitly or explicitly ensure that our coroutines allow others to run. There is a special case of a coroutine, which is a subroutine. Now, this is just for completeness, but if we keep the previous example in mind, where each coroutine yields to the other, we can also ask ourselves whether doesn't this look similar to what we already know about subroutines. But instead of yielding to the other one, we just call the other one. Now, this works beautifully in pseudocode. We all know that this does not work in practice, at least not in any language that has a call stack. It would quickly exhaust it. But this is a special case of a coroutine. From a theoretical point of view, we can either say that a subroutine is a subset of a coroutine, or we can say, the other way around, that a coroutine is an evolved subroutine. Now I give it up to you to choose which one. But the principle is the same. It's about giving the opportunity to other pieces of code to do their job. Now, I mentioned initially that there is a repository with code. If you want to check it out, you have the URL on screen. I saw some laptops going up, so I'll just talk for another couple of minutes to give you time to load it up. And what we are going to do next, we are going to see some, I'm going to show you some demos and talk about some coroutine features, especially for those who have not yet worked with coroutines or don't really work with Kotlin. We are going to start with the basics. But even there, by experience, some things can be quite surprising. And the interesting part, at least to me, honestly, the interesting part about coroutines is that what we today call coroutines, at least in Kotlin, has been invented conceptually some 50 years ago, if my math holds, somewhere in the 60s. But the hardware just wasn't there to keep up. This technique of running some code and then deciding it's time to give the CPU away to run some other code was built or invented, designed back in the 60s, because if you think really hard about it, it wasn't that long ago that we got processors with multiple cores able to run multiple things at the same time. Back then, if you wanted to run 3 things at the same time, you would get 3 computers. Then you would run some network cables, or if you were not lucky, some serial cables to try to coordinate things. And that was painful. So if you wanted to do several things in one CPU, then you needed a way to actually switch among them. And for those who have had the pleasure or the displeasure of running any version of Windows up to and including Windows 98, then you are already pretty aware of the consequences of a cooperative system not cooperating. It was very easy to freeze those machines, especially at the UI level, because, well, they were mostly cooperative. The real multi-threaded Windows versions, they actually started with Windows NT back in the days. All right. Of course, after this, when you decide to go deeper in coroutines, obviously the documentation is always your friend, and it is updated. And now we take a look at how exactly do we declare coroutines in Kotlin. Now, there is something that is going to show up a lot throughout this presentation and throughout the time that you spend writing coroutines, which is the concept of a coroutine scope. For the time being, let's just say that a coroutine cannot be called outside of a piece of code or a scope that has been explicitly prepared to work with coroutines. Remember that I said earlier that it is the Kotlin runtime library who is responsible for keeping up with the state of each coroutine. Therefore, we need to ensure that we have the correct construct in the code. Now, the simplest one is declared with the run blocking method. The run blocking method, as the name implies, it not only declares a coroutine scope, but it also runs some code inside that scope in a blocking manner. Blocking because a call or an invocation of the run blocking method does not return until all coroutines inside that scope are finished. Do we need to worry about it? No. The runtime is going to keep track of everything and is going to ensure that run blocking only returns when all coroutines are done. This takes care of the problem of declaring the initial coroutine scope, which I would say that most of the time, if not always, the first scope needs to be created with some sort of blocking mechanism because, well, the JVM picks up our code on a normal thread. We need to prevent that thread from stopping. That's pretty much it. There is also a possibility of running another coroutine concurrently. That we can do with the launch keyword. It is, well, I'm not going to say that it is strictly equivalent to launching a thread, but for the time being, we can think of it as if launch was creating some other thread. In fact, it is creating another unit of work, another coroutine that is going to do something concurrently with the other coroutines on the system. Finally, the declaration of a coroutine is done simply by adding the suspend keyword to the method declaration. This tells the Kotlin compiler to build up everything that it needs to build in order to run the coroutine. It also means that this function has been declared as a coroutine, therefore it can only be invoked from inside the coroutine scope. If we try to invoke it from any other location, we will get a compile time error. Now, this also means that we get some code. Now, this is functionally equivalent to what we have. Let me just change this for a bit. Let me remove this declaration of a coroutine. Let me run this, and hopefully the result is what we all expect to see from a sequential program. We have hello world. Nothing special. Before we actually do something, now I was going to switch this to threads, but let's stick with coroutines for a little bit. Now, I've been talking about concurrency. I've been saying that coroutines are concurrent, normally, and not parallel. So, if we run this program, is the result going to be equivalent? Who thinks that we're going to see hello world? Okay. Now, this may come, I saw a couple of hands, this may come as a surprise, because what this program is going to show is actually world hello. Now, why does this happen when using coroutines? Coroutines are concurrent. If they are concurrent, they don't run in parallel. Now, if they don't run in parallel, then how do they run? When we start a coroutine, it doesn't necessarily start immediately. I mean, there are some parameters we can specify, but using this construct, the coroutine does not start immediately. It is simply, I don't want to say scheduled, but well, to the lack of a better word, it is scheduled to be executed at the next possible moment. And the next possible moment is a suspension point. We're going to see what the suspension point is a bit later on. But when running concurrent code, because the code is cooperative, that means that the code needs to give opportunity to others to run. In this case, the little bit we have on screen, the only opportunity the new coroutine has to run is when the previous one finishes, which means println world is executed, the first coroutine that was started inside this run blocking scope ends, and the second one can finally run. When both complete, then the program completes. Which means if we, let's just call them H and W, basically what we have is that the W code runs, and then we get the hello code running as well. Now, an interesting bit of trivia. If you may be annoyed at seeing the screen jumping up and down, and that's the side effect of being used to a full-size keyboard. But now let's use threads. And now the result is going to be exactly the same as the coroutines. But in this case, it's not because of any cooperation between them, it's just because the thread had not been scheduled to run at the time where world was printed. Which is why, if we want to give it some time to actually run and do something, then we need to stop or pause the thread, the main thread, for a little bit, and then we have hello world, because then the thread we created had time to run. Now, if we leave that sleep over there, and we recreate the run blocking code, and we launch a coroutine instead of a thread, the IDE is already giving some sort of warning there, because if we run this code, we get again world and hello. Because the only thing that this thread.sleep invocation achieved was to stop the execution of the, or let's just say to pause the execution of the first routine. And because it was paused, the other one, the hello coroutine, it cannot run. The execution is blocked and nothing else can run. No other coroutines can run. There is no cooperation. If we want to cooperate, then we can use the delay coroutine, and you will notice that, squiggly on the right side, that's the IDE informing us that calling that function actually represents a suspension point. And now, when we run this code, we finally get hello world. The difference is that when we were using a thread and we inserted sleep, we were affecting the timing of execution on both flows. They were running, as far as we know, parallelly. With coroutines, with this little change, getting from sleep to delay, we are not working with timings, but we are working with the sequence of execution itself. When we called delay, we told the runtime, okay, this is a suspension point. I don't need to do anything for the next 500 milliseconds, so you can allow someone else to run instead. That's what we got here. Now, because we have seen already both threads and coroutines, they are, well, stateful, right? And because they are stateful, it means they consume memory. No-brainer. Because threads are an operating system construct, and in this context, I mean software threads, each thread, besides the amount of memory it needs to work, and by this I mean the call stack, I mean local variables, it also consumes memory at the scheduler level, which is built on the kernel, and depending on the operating system, you may or may not have a hard limit on the number of threads allowed at the same time. So you also have extra resources being used at the operating system level. Threads also require context switching. Context switching is what I was describing earlier. Save all the register processors, save all the registers from the processor, save the actual processor state into some memory, go to memory, restore the processor state, load the program, and keep it going. This is a context switching. It means that it needs to actually stop the processor to change its data. So it takes time. From a human perspective, it's instantaneous, but from a machine perspective, it's painful. A coroutine, on the other hand, because it is purely a software construct, in this case in the Kotlin runtime, then it consumes its memory for its state, and that's pretty much it. Now, we have another sample. Here we are going to play a bit with different amounts of threads and coroutines, and we are going to see the result. The outcome may or may not be interesting. Now, we start with a bit of code that is going to launch 100,000 threads. Each thread is going to wait for about a second, print a dot, return, nothing fancy, just some busy work. And now we are going to see that this, yeah, it's still running. Still running. Still running. Oh boy. Thankfully, this operating system does not have a hard limit on the number of threads. We might be in trouble, but it's still running. And yeah, still running. Continues, and it stopped. Few seconds. Doesn't sound much. After all, we did launch 100,000 threads that were sleeping for a bit. Sleeping is not exactly the same thing as being CPU bound, but it's the closest we get to. Well, let's just give it a try. And now let's change this into a run blocking scenario. We switch. This, of course, now IntelliJ is telling us sleep is a no-go, so instead we use delay. So now we are going to launch the exact same 100,000 coroutines with the correct constructs, and hopefully we will get a different result this time. Well, the result is that we are done. The whole point of this small demonstration is not necessarily to show that a program using coroutines is faster. The whole point is to show that from a computational perspective, this kind of construct is much more efficient than using a thread. In fact, this took only more time because the IDE had to buffer the standard output, but that was it. Everything was executed in about a second. Looks nice. Now, as we saw, especially on the first demo, that if we had kept the thread.sleep call, then we were not giving the opportunity to other coroutines of running. And as we also saw in this demonstration, that we replaced the sleep by a delay, and then everything ran beautifully. Those are the definition of suspension points. And what kind of suspension points do we have? Well, we have an explicit yield call, which literally means go do something else. We have the delay call. That one puts a little bit of an extra burden on the dispatcher. It kind of wants to give control back after that amount of time. Or a call to any other coroutine. That is also a suspension point. To show how cooperation is important, there is also an interesting exercise. Now, this one is a little bit more involved, because in this case, there is in fact an algorithm used, so we don't need to work with sleeps, and we can show that indeed we have something that is CPU bound. And this algorithm is, well, the sum of the Leibniz series. It's used to calculate an approximation of the value of pi. It isn't really relevant for this point. I just wanted to find an algorithm that could be easily decomposed, and it turns out to be fun, having chosen an algorithm that approximates the value of pi, getting to the hotel yesterday and finding out that I got room number 314. You know, I'm not superstitious, but sometimes it feels like things just work out. Now, if we just run this sequentially, it says there is a time measuring code here. We measure the time in milliseconds that it takes to calculate the pi. It approximates to 314,159, blah, blah, blah. Looks about right. Takes about a second and a half. And we did run a warm-up cycle before, so that we don't get timings that vary too much, you know, the basic stuff of profiling. So running this piece of code sequentially, it takes about, let's say, a second and a half to approximate the value of pi. Now, the first thing that we can show is that we don't need to change the insides of the sum Leibniz function, but because this can be decomposed, then something that we can do is to just fire up some threads to calculate pi. Sure, why not? Now, the Leibniz series can be decomposed, so let's just let me just leave this comment with the correct value of pi to 16 digits, so we can compare at least the first ones. And of course, this is an approximation, so it's not necessarily going to be 100% correct. Simple thread decomposition without worrying much about memory synchronization. So let's just create here an array. We said we were going to, of course, that something was missing. We said that we were going to create some threads. Let's do so. The easiest way is probably to create an array of 10 thread descriptors, and then we start a thread here that just starts with the first small chunk of work, and then we just repeat this thing. All right, we take one off, and we need, of course, to say that this is a long. We are firing threads, which means that we need to wait until they complete. So we need to join on them. I was almost forgetting to store the result, the partial result of this calculation. So now, yeah, this should do it. And now we have val pi, which should be the sum of all factors times 4. We print this on the screen, and we should be fine. Well, looks good. Let's run the thing. It should take a couple of seconds. And of course, with all live coding, this was growing exponentially, which is really not a good idea. We would be stuck here for a very long time. Okay, now it's good. So 3.1415592, that looks about right, a good approximation. And this time it took 244 milliseconds. Nothing special. This is expected. Now, let's try to do the same with a coroutine construct. The calculate pi function already had a coroutine scope, so I don't need to type it in. Can use the same technique, just launching a coroutine here, and then joining, and okay, I don't need to do anything else right now. So what is the result? The result is that it still takes a lot of time. We get an equivalent result as we had previously when we ran this sequentially. Now, this should not be a surprise by now. But I did mention before that we need to give time to the other coroutines to run. So maybe if I added here a yield call, just calculate something and then let the others calculate, this might help. Okay, so now the IDE is complaining. Well, the yield is being not called from a coroutine. Now it is. Okay, we have the nice squiggly there. Yield is now a suspension point. And we have lots of suspension points. Launch is also a suspension point. Looks good. Let's run this. Let's see what happens. The warm-up. Okay, let's format this nicely. Okay, so we now have the hand blocking. And now you have evidence that we cannot call a coroutine from any other scope. Hand blocking. Okay. Well, this is taking lots of time. So basically what's happening here? If you look carefully, let's allow it to run for a little. Maybe it will finish before I complete these sentences. In this bit of code, I have chosen to use a log4j logger because it allows us out of the box to see on which thread, and yes, in this case I mean thread, the code is running. And the thread name, 45 milliseconds, that's painful. The thread name is after the timestamp, which means, looking at this, all the coroutines, you will notice that the call to the logger is at the beginning of the sum Leibniz function. All coroutines started on the same thread. Because they started on the same thread and they are CPU bound, if we add a yield call at each small step, then basically what we are doing is to increase the amount of work that needs to be done on the main thread, because then you need to save this coroutine state, restore some other coroutine, call the other, and then allow it to call this times 1 million or 1 billion times. It takes lots of time. Now, you may ask, okay, but does this mean that coroutines are useless? No, it doesn't. There is an example later on where we talk about thread affinity, where we can see ways to make this a bit different. However, it only goes to show that just because we have a hammer, it doesn't mean that everything is a nail. So if you do have work that is CPU bound and purely CPU bound, then probably you do not want to use it with coroutines that share one thread to run. We all know that the advantage of using coroutines is that you don't need many threads, but sometimes you do. And this is a good example of it. Now, how could we improve this a little bit without worrying about threads? Well, we could use the old trick of not calling yield every time. Let's just say that we call yield every 10,000 times or so. It's going to improve a bit, but well, it would be better if I had not forgotten the number, and of course now it's complaining again. Come on. There we go. As I was saying, we can improve a bit by reducing the number of calls that are being done. But because we added an extra call in between each calculation, then of course it's going to take longer than the sequential method and 10 times as much as the version using threads. Can we work around this? We can, and we will see ways to do it later. Now, cooperation is indeed important. But launching coroutines without caring whether they finish is also a little bit like launching a thread and not caring about whether it finishes. There needs to be a way to control execution of coroutines. Now, let's suppose that we have a coroutine that we launch. And we already know that operation is going to take a long time. It doesn't really matter why, but it's going to take a long time. In the meantime, we have another coroutine. It keeps on running. And for some reason, we decide that we need to cancel everything. If we were using threads, normally we would design our own cancellation mechanism. There would be probably some kind of flag in some shared memory that the thread would check every now and then to see if it could continue running. And if it couldn't, then it would clean up and terminate. We could, play our luck and use the JVM mechanisms to interrupt a thread. And then, of course, the thread implementation would have to know that it would be interrupted. And also it would need to know that interruption meant that it had to stop. But thankfully, the Kotlin runtime allows us to have a method that explicitly cancels a coroutine. It's already built in, yay, and we just need to invoke it. Now, there are, of course, some caveats. Like everything, cancellation is cooperative, and because it is cooperative, it only happens at suspension points. For example, think about yield. Think about calling another coroutine. It may be possible to also use a special attribute of the coroutine job interface, which is called isActive, depending on how things work. We'll see that in a moment. But what I really want to hammer through is that when we call launch, we get an instance of something called a job. And that's something, besides the join method that we can also use with threads, it also has a cancel method that we can use to cancel the coroutine without needing to write more code. Now, let's just look at some more code. In this case, we are still working with the Leibniz sum because, well, it is CPU bound. 3 seconds. You will notice that this version already has the yield call. You will notice that calculate pi is hand blocking. So I said this took 3 seconds. Now, the question is, can we cancel this? Well, let's see what happens if we cancel this thing. So let's launch the whole calculation and showing of the value of pi on a separate thread, or sorry, on a separate coroutine. I'm still thinking about the thread names from before. Let's call it Leibniz. Now, it was 3 seconds, so let's give it about a second. Let's give it about a second, and let's cancel the thing. The expected result is that the application just ends after 1 second and does not print the outcome of pi because that value is only shown on screen when the sum Leibniz coroutine completes, and it never completed because it was cancelled. Now, there is another interesting detail, which is that we are working on this instance. This Leibniz variable contains an instance of job. This job describes the first coroutine, this one, but we did call a second coroutine. Looking back at threads as an example and how we would have to do this manually, if we would cancel only the parent thread, that does not mean that the children thread are also cancelled. Now, in this case, it does. This is called structured concurrency, and there are more features that also help with this. But the big advantage is that the suspension point that actually caused the cancellation was inside some Leibniz. Now, I am a bit ahead of myself. I did mention earlier that we could use the isActive. Hold on a second. Let me just replace this everything. Okay. I could just use the isActive. That's not what I want, sorry. This is not what I want, this is what I want, and it says, interestingly enough, that this is already deprecated. Now, the fun part is that you may still see isActive on older coroutines. It has been deprecated because it is indeed internal code. And it doesn't really work well with this kind of construct. Because just checking the value of an argument, or in this case, just checking the value of an attribute is not per se a suspension point. And hence, because in these examples we are already working with CPU-bound coroutines running on the same thread, sharing the same thread, not using a suspension point would just not work. Now, we still have quite a lot to go through. The next example that we can take a look at, still in the context of cancellations, is the with timeout construct. Let's just put this back in, okay. And I think, now looking at the time, I think that it would be best if we took a, let's just say a 30-minute break to stretch our legs, get a cup of coffee, heed the nature call, try to wake up a bit, and then continue with some additional details on coroutines. I hope that you enjoy that idea. See you in 30 minutes. All right, I hope that you all had a nice break, stretch your legs, got some caffeine to help with the remaining of the session. And I was, before we go and take a quick look at the timeout functions, I got a question during the break, which was very relevant. We were talking about cancellation and suspension points, and eventually I removed this line, the yield, so just as a quick refresher, as long as, oops, bad import, bad. As I was saying, as long as we have that suspension point there, then the calculation is going to be cancelled. However, the moment we take that suspension point out, then the calculation is not going to be cancelled anymore, because the dispatcher does not get control back. This goes to show that the even cancellation depends on the collaboration between coroutines. Now, going back to the timeout, there are, of course, well, there are two flavors. Either we get a timeout cancellation exception when the routine times out, or we have a null result. And this is, you know, simple to demonstrate. We can just remove this delay over here. We say that we want to run this with 1 second timeout, and of course we don't get a job anymore. Instead we get some result. The simple function call is going to throw an exception, and exceptions are handled in the normal way, even when using coroutines, and it goes without saying that now with timeout or null, it's going to return a null value, so we can know the coroutine has been cancelled. Nothing too fancy. Now, so far we have launched other coroutines, and I've been always mentioning that they are concurrent. But just starting a coroutine is, well, it's a bit like writing functions that return nothing all the time. Not always useful. If we want to get some result out of a concurrent coroutine, then we can use the async function instead of launch. Now, the big difference is that in this case, we are going explicitly say that whatever it is that we are starting, that we are launching, is expected to return a result. Async by itself does not mean that whatever it is that we are launching is going to run in parallel with the code we are writing. Now, launch returns an instance of the job interface. Async returns an instance of the deferred interface. Both allow us to control execution of the coroutines. The second allows us to get the result back. And since right now what we are trying to do is to get information back from a coroutine without resorting to shared memory, like, for example, what we did a couple of hours ago when we were playing around with calculating pi, and we used that trick of having each thread and then later each coroutine write to one position in the array so that we don't need to worry about synchronization. We were sharing memory there because at that time we were not using async to get a result back from the coroutine itself. Now, in order to go explicitly concurrent, well, this is not a big deal, right? But this time, just to get away from pi and to get away from CPU intensive and CPU bound coroutines, let's do something different. Instead, let's call a web service. Now, this is just something simple. It's an API out there that returns translations of hello in multiple languages. So nothing fancy. This is using the Fuel library, but it's not relevant for what we are doing here today. It works. That's also proof. The Devoxx Wi-Fi is working. The idea now is to, first of all, establish some benchmark. We see it took about a second. Let's run this just 2 or 3 times. We're not proving anything, just getting a feel for how long this API is taking to respond. It's taking about 1 second. And now, let's try to get some other languages in sequence. And of course, we will see that I don't know, Italian, for example. I did not did not type NL because I know that they don't have, for some reason, anything in Dutch. For some bites me. It's not going to surprise anyone if we see that this takes longer. Took about 2 seconds. Now, if we do this time asynchronously, let's not be fancy and let's just let's do this the old-fashioned way. No fancy constructs. Let's just do the old one variable, one thing. It will also help to show that indeed all of these invocations are going to return a deferred. Let me delete this one, and not useful. And this time a nice set of Romanic languages. And of course, if we leave it at it, then we get nothing. 1, 2, 3, 4. And now if we want the results, we just await each of the results. All right. The whole point is that now we got all languages in the same time it took us initially to get one. Now, this was so easy compared to what we were doing earlier with the approximation of pi. Because now we are using an I/O operation. And on top of an I/O operation, it's a network I/O operation going probably halfway across the world to get the difference, to get the result. That in itself is a suspension point that was implemented by this fuel library. You see the squiggle over there. That function is a suspension point that it's going to take quite some time to get a response. Therefore, it follows that even though we are still on the same thread, we are still running everything in one thread, in the main thread, then it follows that if the library is busy sending some packets across the network and receiving and waiting for the reception, there's more than enough time to do something else. Unlike the pi approximation calculation algorithm, which was just dying to get some more CPU time. Now, async also has, just like job, we can also call cancel, like we did before, and we can also call, if we don't need the result, we can also call join, and there are, of course, also the other functions available on the job interface. Let's just to try to drive home the point that async and launch are functionally, well, hold on a second, are pretty much a superset of one another, is that if we do this, the old-fashioned way, and instead of async, we just use launch. Then it can be demonstrated that in fact the only difference between them, or at least the only big difference between them, is that I didn't even need the... I could replace this by a hand blocking, but let's just try to do something equivalent, where we wait for all of them, and the result is going to be pretty much the same. We will get all four languages. We are still going to have to wait the same amount of time as we waited initially to get just one, because launch also runs, or should I say launches, coroutines concurrently, but the difference is async allows you to get a result back from that coroutine. And then it becomes a lot more useful. This is what we have been doing. And now, we touched on cancellation a few moments ago. And we wrote some simple code that simply waited for a little bit and then canceled a coroutine. But in that case, it was the code that launched the coroutine who decided to cancel it for some reason, doesn't matter what. However, what happens if there is an error inside the coroutine that we launched asynchronously or concurrently? Then things get a bit tricky, right? I mean, how many of us, some of us have been working with concurrent and parallel code. Completable futures, anyone? Yeah. And now, of those that have worked with completable futures, did the code I've done that as well, so does the code that we write when we launch multiple completable futures and then need to handle the failure of one of them, that also affects the results of the others, does that look nice at all, or no? Yeah, I didn't think so. Thankfully, instead of having to deal with the complexities of launching a number of threads that are going to do something, and that something may fail, and because if one fails for some reason, then we need to cancel the others, or we need to disregard what the others are doing, it gets really ugly. Thankfully, with coroutines, the nice folks who wrote the Kotlin runtime, they thought about that. And this problem is solved for us with a concept which is called the structured concurrency. Now, structured concurrency is a way of organizing and chaining concurrent jobs, or in this case, coroutines, in such a way that all dependencies are clearly identified, and then failures or cancellations cascade through the entire hierarchy up to some point. If we want to be explicit about and saying, okay, so this is the little bit of code that I want to ensure that is entirely cancelled in case of an error within one of those coroutines, then we create a new coroutine scope. There, we define that group, and, well, what happens within that scope stays within that scope. To demonstrate, let's take a look at some concurrent code. Now, we have two coroutines, very imaginatively called 1 and 2. Number 1 finds the answer to the most important question in the universe, takes about 1 second to do it, and says it's 42. Way faster than the original computer. Number 2, well, if number 1 finds the answer, then number 2 needs to find the question. It says it's 1. We run them. We add the results, and, well, if things work, then we get 43. But now, what happens if one of those coroutines fails? You already noticed that this line was commented out. Let's ignore the unreachable code warning. Number 2 tries to find the question, and as we all know from the Hitchhiker's Guide to the Galaxy, we know the answer to the most important question in the universe, that's 42, but nobody knows what the question is. So it makes only sense that the function that tries to find that question cannot and fails. The result now is that, drum roll, nothing happens. We get this message saying that some coroutines have thrown an exception. But we launched 3 coroutines, or let's not take it too deep. We launched 2 coroutines, right? Using async. We launched 1 and 2. However, 1 did not fail, but 2 did. If we were just waiting for the result, if these were threads and we were waiting for them to complete, if we were using completable futures, then the completable future for 1 would say successful, and the completable future for 2 would have completed with an exception. Which means that, well, with threads, we would still have seen this print line, but we didn't. However, yeah, and the other one that threw the exception also did not print the message. And this goes to show that within the coroutine scope that we created, we launched 2 async jobs, 2 deferred jobs, if you prefer, or 2 async coroutines, take your pick. Because one of them failed, the other one was cancelled. And, well, we had number 1 at a suspension point, which is also a cancellation point, which means that it was stopped. Now, did we have to write an enormous amount of code for this to happen? No, we just needed to declare a coroutine scope and then handle any exception that might have been thrown during that calculation, as we normally would have on a sequential flow. The interesting part about these features is that this code looks like it is sequential, but it isn't. It is actually concurrent. But then it becomes a lot easier to reason about than if we were using threads as before. Now, this is where we are going to spend a couple of minutes on. Thread affinity. Now, until now, all the output we have seen from the code we executed using the loggers, all of those lines have said that the code was running on the main thread. So far, we have worked under the assumption that a program running coroutines is single-threaded. We may want to hold on to that, and we will see why in a moment. But in practice, it depends on the dispatcher. Now, just like operating systems have schedulers, and the schedulers decide what thread runs when and where, the Kotlin runtime has dispatchers to handle coroutines. Now, of course, the dispatcher does not decide who runs when. That's up to the coroutines to have suspension points. But it does decide where to run it. The default dispatcher for coroutines on a Kotlin program is going to use one thread, and that, if we don't change it, is the main thread. There are other dispatchers, we are going to play around a little bit with them, that have different behaviors. And that also means that if we are writing a piece of code, especially if we are writing a library containing coroutines, and we are not sure in which context that library is going to be used, at least my personal opinion is that it is way better to think of the threading model of Kotlin coroutines as being free-threaded, in the sense that your code can be running on any thread, anytime, at any point. This also has consequences with regards to sharing resources, but that's going to be a next subject. And there are at least two dispatchers that we can use, the default and the unconfined. There are a couple more. And let's see what happens when we start playing around with dispatchers. Okay, so now, this is nothing special, right? It's a run blocking block. There's a loop there. It launches a coroutine. It uses the logger, so we can actually see on which thread things are running. Without any surprise, we see everything is running on the main thread. All right. Now, how can we determine, how can we specify a dispatcher? Let's try with the run blocking call. Now we have predefined dispatchers. Let's try the default. What's going to happen? All right. Now we got interesting results. We got different threads. Now notice that the main thread does not appear on this list anymore. We do have quite a few worker threads mentioned. And now we can try to chase a bit a few of the coroutines. That's why we had the before and the and after. Let's see. For example, so thread coroutine number 6 begins on worker number 8 and then continues on number 8. Let's see if we can find something different, because, well, this is not necessarily... here is one. coroutine number 4 started on worker number 6. But now coroutine number 4, after the suspension point, continues execution on worker number 11. This is what I meant when I said that, especially if we don't know exactly how the coroutine is being used, it is best not to make any assumptions on the thread that the coroutine is running, because you may start running on one and then end on the other. Now, we also found out that the default dispatcher is going to use a thread pool to run the different coroutines. Now, let's try a different one. Let's try the unconfined dispatcher. The unconfined dispatcher has an interesting feature. All coroutines start their execution, in this case in the main thread, and once they reach the suspension point, they are resumed on the Kotlin X coroutines default executor. That's where the dispatcher gets its name, in the sense that coroutine execution using the unconfined dispatcher is not, well, confined to the same thread where the coroutine was launched. There are also other dispatchers. Now, this is not going to work. The main dispatcher is not implemented on this runtime. It depends on the platform. You will find, for example, the main dispatcher implemented on Android, where it represents the main loop. It represents the loop with access to the user interface, for example. And there is also another dispatcher, the I/O dispatcher, which, as the name implies, it is meant for I/O operations, and eventually, actually sends work to the default dispatcher thread pool. Now, from a practical point of view, that means we have, outside of Android, we have two dispatchers or predefined dispatchers that we can use depending on the behavior we want. We have the unconfined dispatcher that starts execution of each coroutine on the same thread where it was launched and then resumes it on an executor. And we have the default dispatcher that just schedules coroutines for execution on a default thread pool. Yeah, we can specify dispatchers on the run blocking, and we can also specify dispatchers on the launch invocation. We can do the same with async. We can do the same with coroutine with context. That's another way of just specifying the coroutine context where everything is running. And this takes us back to our nice example. I think we can use this one. My mistake. We can use this one. This is the example of the CPU intensive or CPU bound calculation we used in the beginning. And we noticed that even when we started many coroutines for this calculation because they were all executing on the main thread, well, we didn't improve our performance when compared to the sequential operation, but it got worse. But now that we know that we are not limited to running things on the main thread, we can, for example, do something like this. We can just tell the runtime that we want to use the default dispatchers, and now we are doing calculations on the default dispatcher thread pool, and now we have improved our code performance, or sorry, our program performance in comparison to the sequential operation. And in fact, we got it pretty close, if not identical, to the version we implemented using threads directly initially. Now, another question that does merit reflection is, are we limited to using the dispatchers that come with the runtime? Now, even the default dispatcher, it is a thread pool, but it is limited. The number of threads, it's not going to grow infinitely. In some cases, and now, of course, it always depends, right? It depends on the use case. We know now that we are starting a CPU-intensive calculation, and we want to take advantage of all the boilerplate saving features of the coroutines runtime. Can we define our own dispatcher? For example, can I define here a thread pool that is going to be used specifically for this calculation? Well, as you may imagine, the answer is yes, because the coroutine runtime already brings a nice extension method to the JVM executors class that allows us to convert an executor into a coroutine dispatcher. Now, I really shouldn't do it this way. Let's do this properly. So we create the executor, we spell it properly, because a properly spelled code is always a nice code. We say that we want to use this as a coroutine dispatcher. Now we move our code into that dispatcher, or into that coroutine context, and now we shut down our executor. Okay. Doing things this way allows us to create a set of threads, a thread pool, a JVM thread pool, and use it to schedule execution of our coroutines. Now, you may also ask, all right, but why go to this trouble if I could just launch 10 threads manually like we did at the beginning, wait for them, and do the exact same thing we have here? Well, the truth is that maybe in this specific example you don't earn much by doing this. On the other hand, if you were doing something that required structured concurrency, If your calculation could fail, and then you wanted to calculate all the others, if the calculation would not take 2 seconds but would take 2 minutes, then probably if calculation of one of those factors would fail for some reason, you would probably want to stop the others as well. And in those scenarios, it actually becomes useful to specify your own thread pool. It goes without saying according to whatever scenario it is that you are using. Just if you are not used to it, if you do create your executors, just don't forget to shut them down. Otherwise, you may risk the problem that your program never terminates. Now, a bit of an open question. So, when we write a coroutine and someone calls it, we have no guarantees as to under which context it is being called. But that's something that we already expect. I mean, every single line of code that we write has no guarantees as to on which context it is executing. So we are fine there, no problem. However, we normally know that if we write a function and it starts executing in some context, it's going to end in the same context. Unless we write, going back to the JVM, unless we change some features, for example, and then execution resumes in some other thread. But generally speaking, it starts and it ends in the same context. However, if we remember that this method may be called from any context, and that the caller may define the context on where it is being called, it means that it can start and end on completely different threads. Which begs the question, it is free-threaded, and then it begs the question, what about synchronization? Well, sometimes we do need to access shared resources, right? Let's have a thought exercise for a moment. Let's go back to the single thread example. Let's imagine that we write a coroutine or a couple of coroutines. They need to share some memory, and they need to synchronize access to that memory. Doing a thought exercise, we all know that the traditional Java runtime synchronization mechanisms, they are thread-based. They were meant to prevent code running on different threads from accessing the same shared memory. And that means that if we set up a synchronized block, for example, in our coroutine, and we have multiple suspension points inside that block, and the truth is that the moment we call another coroutine, especially if it is not implemented by us, then we have absolutely no idea how many suspension points are down there. We saw earlier on in our examples that when we were calculating pi, that our little coroutine would call the calculation one. That call itself was a suspension point, but then inside the calculation there was another one. And when we called cancel, it would cancel on the second. Now it goes to say that when we call another coroutine, we have no idea how many cancellation points are there, or suspension points, or whatever. By not knowing how many times the coroutine is going to be suspended, we also have absolutely no idea of the context it's coming back. So if we define a synchronized block, we start on thread A. The synchronization happens on thread A. If we then try to release that synchronization from thread B, well, that's not going to end well. Especially if, for some reason, then we have concurrent access to the same block from different threads. And then they try to release it from other different threads. By that point, we have two scenarios. Either we are deadlocking threads on our executor, and then execution of our coroutines grinds to a halt, or everything appears to work because everything happens on the same thread, and therefore the synchronization mechanism has nothing to synchronize. The bottom line is, because the traditional Java runtime engine synchronization mechanisms are thread-based, they do not work properly when we write a coroutine. How do we solve this? Well, the first solution is, of course, the same one, the same advice to all concurrent parallel code: don't share resources. Simple enough. Sometimes you need to. One solution, may or may not work, is to run all the coroutines that share the same resources or the state or whatever in the same thread. Now, in that case, we can use the same trick that we did before with the Leibniz calculation, and we can use the with context method to simplify a single thread context. Under the hood, it's going to create one thread just to run that scope, and then we guarantee, okay, everything is running on the same thread, no synchronization problem there. This only works properly, naturally, assuming that the coroutines suspend and block on I/O, for example. Otherwise, we get the same issue as we did with the Leibniz calculation. There is a mutex implementation written specifically for using on coroutines, so that one you can use. It is coroutine aware. And finally, another possibility is to use channels. Now, channels are used for message passing between coroutines. It may help. Message passing, well, it is message passing. One entity produces something, the other one receives it. Nothing special about that. Channels allow you to fan out or fan in, which means that one producer can have multiple consumers, and also more than one producer can write to the same channel. Channels are fair in the sense that the implementation attempts to ensure that whoever is waiting and waiting first gets a message. And they are extremely easy to use. You create a channel simply by instantiating the channel and specifying the type of messages you are passing, and then you call send and receive on each channel. Now, let's just again take a look at how this works. So now we have a completely bare main method. Let's create a nice channel. This time not being, could be probably original. Let's call it names. And let's say that this is a channel of string. I just want an instance for now. Thank you. And let's just say that now I have one. Now, do I want to do this? No, let me do this inside here, just so we can have that nice logger over there. So we launch now one coroutine. This coroutine is going to send some names. For example, Sarah, John, I don't know, Mary, Bertian. I probably should spell it correctly, otherwise someone may not be happy. And let's just, for each, let's just send let's just send it to that channel. And now let's create another coroutine that is going to receive the names we are sending. Sounds pretty straightforward. And there we have it. Now, this is interesting, you may ask. The application did not stop. Oh. Now, channels have an interesting feature, which is that as long as they exist, as long as they are operational, then you can always attempt to read something from them. Channels can be used, therefore, to implement hot sources. Unless you are, if you are not familiar with this terminology, a hot source is a source of, in this case, messages that does not necessarily end. It's potentially infinite. And that's what a channel is. A channel is a potentially infinite source of messages. Now, that was the reason why it was necessary to close the channel so the second coroutine would terminate, because otherwise it would be suspended at the beginning of this for loop indefinitely, waiting for the following message. Now, one thing that we can now try to do is to attempt to demonstrate the fan out feature of channels. Let's just, well, I really did not want to use copy paste. So let's suspend fan receive. Let's use the channel interface. Yeah, let's use the channel interface. And of course, I think I'm writing Java, which is always a problem. And let's get some identification for this consumer. And let's say that our nice consumer. Now I am writing Java again. Now you can probably already guess which language I have been using more in the past few weeks, right? So apologies for that. Now, so yeah, let's launch receive from names and call this one A. And let's launch receive from names. Call this one B. Now the result, hopefully, if it doesn't work properly, I'll have to add a couple more names. But no, it is. For whatever reasons, A got the first 3 names and B had to content itself with the last name on the channel. This is an example of fan out, and we can have a similar example with fan in, which is, well, which is just the other way around. I mean, it's not so tough. There is an experimental API allowing us to explicitly define a producer, which is called of course. Come on. Oh. Apologies, I'm so used to having the run blocking call on the main thread that I often forget it's there. So let's just copy paste this one. We don't need to specify a type here. It's going to be happy the moment we send it. It's now complaining, saying that we need to call send, and now we need to opt in for the API. That means we need to add a specific annotation telling the compiler that we are happy that we are using an experimental API, and being experimental, it can change at any moment in time, but it is still fun to use. So now this becomes our channel. This becomes our channel, which means now we can get rid of this. There's a compilation error here, which means that when we use the producer function, then we don't have a full-blown channel anymore. All that others can do from that channel is to receive information from there. Therefore, we change the type here, and then we have something that has the advantage of being explicit about what it is doing. It is only receiving information from the channel, and now we are done. Also, notice another detail. We don't have a close function call here on the channel, and yet the program terminated. This is because when we are using the experimental produce method, as soon as the coroutine started by, or the producer coroutine that was started completes, the channel is closed automatically. Now, this is indeed one of the solutions to solve the concurrency problem.
It's still single-threaded now.
Sorry?
It's still running on the main thread.
No, it actually says that the process has finished. Oh, you said it is running on the main... Sorry, the question was that it is still running on the main thread. It is indeed. It is using the run blocking call without specifying a dispatcher, and therefore it is running on the same thread. I'm not sure if that was your point.
Could you change it to use different threads?
If we could change to use different threads, definitely. We can do that, for example, right on the run blocking invocation. For example, we can send it to the default dispatcher. And now we wait a bit until it completes. And there we go. This time it's running on the default dispatcher thread pool, and well, scheduling permits that the receivers do this time run in parallel on different threads, and therefore each one of them has had the opportunity to pick one from the channel. So we can indeed specify where everything is running, and we can even do some different things. We can even be more specific and say that only the receiver B shall run on the default dispatcher, on the default thread pool, and then we have this kind of constructs. Basically, all or most of the methods that allows us to create a coroutine scope, they allow us to specify what kind of dispatcher we want to use. Therefore, we can play around either with the default dispatchers or with thread pools we have defined. Okay, thank you. So, this goes to show that dispatchers are a way to send and receive messages between coroutines. This does not mean necessarily that one could be less careful with writing concurrent code. I read some time ago that a study has shown that in Go, in the Go language that uses message passing to a large extent, the amount of concurrency errors related to message passing was not substantially lower than when using synchronization or other shared mechanisms in other languages. So it looks a lot simpler, and it is indeed simpler to reason about, but it still needs to be taken with some care. Now, there is also a special case of a coroutine, which is a generator. From an abstract point of view, a generator, well, as the name implies, it creates things, it generates things. But unless, or unlike other coroutines, that's its only job. That's the only thing it does. It's producing things. It only yields to the caller. It yields to no other coroutine. And the only reason it yields is to produce a value. Generators are implemented in Kotlin as flows. A flow is created with using the method flow from the coroutine scope. It yields only when the code inside the flow is ready to emit a value, and it will allow collection by other coroutines. The interesting part of flows is that flows are data streams. They can be compared somehow with streams in Java, for example. Others compare it with observables in Rx Java. And they are called. They are used to emit a finite set of data, and they only suspend when the generator coroutine suspends. They suspend in no other circumstance. Because they are data streams, there are intermediate operators that can be defined on flows, such as map, transform, take, or zip. And they are transparent to exceptions, meaning that if the generator or any of the mapping functions throws an exception, then that exception is propagated throughout the call stack to the initial caller. And they complete, of course, when the data ends or with an exception. Now, we may create a flow that provides some data. In the interest of time, I am going to just use the same API we used before to create a flow that produces the translations of hello in a few languages. Now I just need to remember exactly which one that was. Here it is. I am going to copy paste, which is always fun. So nothing too special about this. And now we just create a new hand blocking scope. Make it easier. We create a flow and we say that for a couple of languages, let's just use one or two. We are going to emit the language code. This is it. And now, of course, we can map, let's say we want to make it uppercase, and now we collect all of them. And hopefully this will actually work. There we go. You will also notice, I'm not sure, yeah, it is visible. Let me add just one or two so it is easier to see. I wonder if we are going to get yeah, yes, we did. You will notice that there was a substantial or a visible delay between each element. And that is, as I mentioned earlier, flows only yield to their caller, and flows being called, they don't generate all items beforehand, but only as they are collected. And in this case, we are emitting one at a time. Emitting one at a time, we have no parallelism in here. Therefore, every single element was placed by itself. Now, this goes to show that we can have in Kotlin using coroutines both hot and cold data streams that may or may not, depending on your use case, help solving concurrency and synchronization and resource sharing problems. Now, we have a few minutes. Maybe it is not enough time to build the entire Webflux example. So I will ask your patience as you bear with me for a moment while I just exit presentation mode to change to the branch. I'm cheating a little bit. In the same repository, you will find a branch with proposed solutions to all the files I have been changing today. And I am just going to check out this exercise, this version. There we go. The interesting part about this, now I can go back to the presentation mode and you can go back to reading my screen. Thank you for your patience. The idea right now is to compare the implementation of a REST service using your traditional Tomcat-based, servlet-based synchronous implementation, and another one using Spring Webflux, which already supports coroutines and allows a concurrent implementation. What you have on screen right now is the implementation on the reference server project on the repository. And this is your, normal run-of-the-mill standard server. You will notice that it has one endpoint /names, it returns 3 names, and whatever it is that it does to retrieve those names, it takes 500 milliseconds. The Webflux implementation is not much different. Let's forget the names flux for a moment. Let's look only at the same implementation for names. Same thing, except that now we have a coroutine, and instead of a sleep, we have a delay, which means, as we already know from all that we have seen today, that this allows the coroutine to relinquish its CPU time and give time to someone else. As you can see, there aren't that many differences. As such, now you may ask, all right, so in terms of implementation, there aren't that many differences. Okay. And what about performance? How does this compares? All right, let's take a quick look. And now, all right. So now let me just start the reference server. It should be running in a couple of seconds, hopefully. Yeah, here it is. And now I have an installation of Kotlin pre-configured with quite a few tests. There is one that is relevant for this purpose, which is number 7. It is going to run a simulation. Basically, what it is going to do, it is going to fire a nice amount of requests, 15,000 requests to the server I have started. And the whole point of this exercise that we are doing now is to show how different can two implementations that were written by us almost in the same way can be different when using two different, not only two different runtimes, but also two different work balancing mechanisms. Now, this is almost done. Let's take a look at the report. Now, you remember, I believe, that this implementation sleeps for half a second before returning the list of names, which means that from a theoretical point of view, we would expect that each call to this endpoint would have a latency of about half a second. Looking at Gateling's report, we see that indeed the minimum response time is half a second. Looks good, but the maximum response time was 8 seconds. In fact, according to Kotlin, the mean response time was 4 seconds. What this suggests is that the default configuration for that server just did not have enough threads to serve this number of requests, so it had to queue those requests, adding a lot of time to its latency. The question now, of course, is, does it get any better if we use a version based on coroutines? Let's keep in mind, let's remember that the whole purpose of coroutines is to have some sort of lightweight concurrency. I'm not going to call it lightweight threads because that has been taken. That's what Project Loom is implementing. But I will just say that it is a way of getting a lightweight concurrency mechanism working. And we have our Webflux server up. And now comes the moment of truth. Notice I have not changed them, but you can, I hope, trust me when I say that both implementations use the default settings. It's just the project from Spring Boot Starter, putting it there, defining the endpoint, done. No special configurations. All right, so the exact same test, this time against the Webflux implementation. It should take a couple more seconds, hopefully. Drum roll, please. There we go. And now we see that indeed, surprisingly, the minimum response time was 500 milliseconds. And the mean response time was 503 milliseconds with a maximum response time of 800 milliseconds, presumably, I would say, in the beginning when the JVM still had not warmed up. I believe that this shows that as long as the coroutines we are using, and now let me just change this implementation here. There we go. As long as the coroutines we are using do have suspension points and are indeed capable of relinquishing CPU time to other coroutines, then that we can have quite effective implementations that use very little threads and yet can do approximately the same or even more work that a similar implementation using threads would. This example with the web servers is functionally equivalent to the one we did in the beginning just with hello world, just with a simple for loop, and you can see the same kind of difference on this case. Now, unfortunately, we do not have time to go deeper, but I hope this 2.5 hours have given you a little bit more about Kotlin, a little bit more about coroutines. I hope that it has answered any questions that you might still have. And speaking about questions, we have 4 minutes left. Does anyone want to ask something at this point? Maybe, just maybe, I have an answer for you. Yes?
Do coroutines work with transactions? They have to stick to single thread.
I am sorry, I didn't quite catch that. You said if coroutines...
Do they work with transactions?
If they work with transactions. That's what you mean. Are you... Okay, the question is, do coroutines work with transactions? Do you mean Spring transactions? All right. Now, as you know, and I suspect that the reason you are asking that is because working with transactions in Spring across threads is a pain. And, well, if you use coroutines in a single-threaded executor, beautiful, right? Because you never leave the same thread. So if you create the transaction already inside that executor on your first coroutine call, for example, you're good to go because you're not leaving that thread. Fine. Now, if your coroutines context gets switched, or if you, for some reason, use a dispatcher with a thread pool, then you're back where you started. But as long as you can ensure that the coroutines handling the transaction are always running on a dispatcher that is confined to the same thread, you should be fine. Yes?
You use coroutines with multiple threads. Don't you get also the context switch?
All right, the question is, if you use coroutines with multiple threads, don't you get also the context switching? Yes, you do. Yes, you do. Now, the question is, why can that be an advantage? It depends. Let's say, for example, okay, a good example was this performance test we just saw with the Webflux server. We sent 15,000 requests to it, and it surely does not have 15,000 threads. The behavior we saw with the normal or the traditional implementation using a thread pool was that it had a latency up to 8 seconds. Now, the second, it also has a thread pool based on coroutines, but because it was using coroutines, those threads were used more efficiently. So my point is, you do have context switching, yes, but because not all coroutines will necessarily change threads, then you get a more efficient use of the threads. They may switch, but they don't necessarily stop doing nothing while waiting for something to happen. I hope this has somehow answered your question.
Yes.
Thank you. And time's up. Thank you so much for coming. Continue doing your thing with Kotlin coroutines, and we'll probably meet again on the floor. Have a great day, and I guess it's almost lunchtime. Enjoy. Thank you.